again. Sorry, I'm late again. Okay, so today I wanted to go through homework 3 with you, answer any questions you have about that, anything you wanted to ask about homework 2 that I handed back last time, and kind of answer any questions for the final. What I'll say first is I am hoping to make the final a bit closer to the homeworks this time than last time. I recognize the material didn't match as well as I wanted, and as well as I guess you probably expected. So I've not graded your second critical review assignment yet, but we'll get to that. So any questions up front before we get going? I think the exam's Thursday at noon, if I'm remembering correctly. I did just double check it recently, and I put them in my calendar. It should be Thursday at 12:30. Yeah. All right. So, any questions or issues?
How long will the test take?
We have 2 hours for it, so I imagine I'll probably make it about the same as last time, and so I guess you might have a little extra time. Maybe I'll put a part of maybe a tiny bit more of a question, but probably not. I'll probably just give you the 2 hours. It'll basically be like last time, a little extra time.
If you want the first exam, I didn't have enough time to do all of it.
Okay. Well, this time, hopefully you will have enough time.
Yeah, I'll try.
Okay. All right then. So let's talk about homework 2 then. So the first problem, number 10-2, and really this is covering some disinfection and advanced oxidation stuff, and then we'll kind of go backwards towards the adsorption after that. And I say backwards because a lot of the material we covered earlier in the semester was particle related, and so coming back to adsorption, somewhere between chemical and particle, and I added it here at the end because I thought it'd be nice to kind of give a full coverage of how we would deal with pharmaceutical or organic molecule type removal. So advanced oxidation, reverse osmosis type stuff, and adsorption are really the primary options. Okay, so with that, situated over here. Okay. So problem 2 says a utility plant treats water supply containing 0.8 milligrams per liter of manganese 2 plus in addition to by the addition of ClO2 to precipitate the manganese oxide solids is kind of their intent. If the reaction converts ClO2 to ClO2 minus, how much MnO2 solid would be produced, and how much ClO2 would be consumed in 1 day of operation at a plant producing 40,000 cubic meters of water per day. Okay, so essentially there's a little bit of chemistry here, and we would need to take a look at the equation here where we have Mn2 plus, and we're adding the chlorine dioxide, ClO2. We also have water involved, and this is going to end up giving us this manganese oxide solid and 2 ClO2 minus if we were to do these balances, we'll find that also releases 2 protons. So essentially, we took the oxygen, 2 oxygens from water. During this process, that means we're releasing some of these hydrogens, and we get the results there. And actually, the hydrogen balance is not making sense. That looks like should be 4, right? Okay. At any rate, what we're getting is some consumption of chlorine dioxide and converting it to ClO2 minus with that reaction. So it's pretty straightforward in terms of 2 moles of chlorine dioxide per 1 mole of manganese. Okay, so with that, we can start approaching the problem to solve for the amount of mass of ClO2 we need. And so we'll need some molecular weights here. We'll get our manganese oxide. That's about 87 grams per mole. If we were to look that up. And then we can also look at our chlorine dioxide, which would be 67.5 grams per mole. What's that? I think so. Okay. So then, in terms of how much manganese solids we're producing, we can take a look at essentially what we're given in terms of the amount it contains, and since we're essentially precipitating all of it, we can say all of this 0.8 milligrams per liter of manganese is going to end up in solids, right? So we can say that 0.8 milligrams per liter of Mn2 plus, and we can multiply this through to end up finding our, just a series of conversions to get to our answer here, given that we have some volume of water per day and it contains this amount, right? So we'll go ahead with multiply it by essentially, and I guess we can add here manganese. For the atomic weight of manganese is 55 grams per mole. Okay, so we can multiply over by 1 mole of Mn2 plus per 55 grams. And, I'm just going to take a shortcut here and say we could just use everything in milligrams and millimoles, and everything will just kind of simplify nicely. So I'm just going to write that there. It's the same thing, right? Could just convert, but I'm just going to do that. Okay. So we also need to multiply through by the molar conversion. So we have 2, again, millimoles of the chlorine dioxide, ClO2, per 1 millimole of Mn2 plus. That's just coming from our stoichiometry here. Then we need to multiply, continuing here, multiplying that by our molecular weight for ClO2, so 67.5 milligrams ClO2 per 1 millimole ClO2. And continue, we want to convert from essentially milligrams into kilograms. So we're going to end up with a pretty large number if we don't. So I'll say, let's see. Yeah. 10 to the minus 6 kilograms per milligram. So that's just taking all the way from milligrams to kilograms. And finally, what I'll do is take that 40,000 cubic meters of water per day and convert that, convert that to liters. So we'll include that amount of water here as 4 times 10 to the 4th cubic meters per day, and we need to get the cubic meters into liters, and then that'll give us, then the liters can cancel with our concentration. So we'll multiply that by essentially 10 to the third, so 1,000 liters in every cubic meter. Okay, so all of those calculations there, all put together, should give us an answer that is, I guess, the first part of the question in terms of how much manganese oxide will be produced. And so that'll give us 78.5. Actually, I'm sorry, that's 78.5 kilograms per day, but that's not the manganese oxide, that's the ClO2 required. I totally skipped ahead. Sorry. So that's the ClO2 consumed. The manganese oxide produced is pretty much the same. We take manganese oxide, multiply it through by the amount that we have there, do the molar conversions, and I realized just now that I completely mixed both parts of my solutions here, and I'm sorry about that. So no, this is correct. Okay, so this is correct for the ClO2 consumption. For the manganese oxide production, we're still going with a 0.8 milligrams per liter. This time we're going to multiply by 87, essentially grams per liter, or excuse me, grams per mole of manganese oxide, the solids. And I'm just going to say milligrams per millimole. And I'm going to divide that right here by the amount for manganese itself, 55 milligrams per millimole, to get that ratio involved to convert essentially from one compound to the other, and then do the same thing where we're converting the liters to cubic meters. And for the flow rate through the system. And then we'll go ahead and convert to kilograms as well. And doing this one, again, kind of plugging in the numbers, this should give us 50.6 kilograms per day. Okay, so not anything that's particularly complex here. It is technically a redox reaction. We didn't really talk about redox stuff, but at the same time, you could come up with this molecular formula or this equation, and the amount of hydrogens that we're producing here didn't actually really matter. It was more just the ratio of manganese and chlorine dioxide. But it does kind of show you, in terms of the application, what would happen here in this type of a case. Okay, so next problem, problem 10.3. It's a little more complex, and we did have, I only asked you to solve for B, C, and D, because A was redox related. And I gave you the book solution for that so that you could have kind of that baseline information in case you needed it. So the problem says a metal plating facility has a waste stream at pH 6.5. It contains 6 milligrams per liter of cyanide, expressed as Cn minus. It is proposed to oxidize the cyanide to innocuous cyanate ion, CnO minus, by addition of chlorine dioxide, which is reduced to chloride in the process. So part A asks about the redox chemistry of that and those reactions. Part B goes on to say, as shown in table 10.3, the oxidation rate of HCN is negligible in comparison with that of Cn minus. If the dose of chlorine dioxide determined in part A is used, which that was given, what detention time is required to oxidize 99% of the cyanide in a CFSTR if the pH remains at 6.5. Assume instantaneous equilibrium with HCN and Cn minus. Okay, so we have equilibrium equation involved here. We have essentially the 6 milligrams per liter of Cn minus, or Cn, right? Cn minus going to ClO minus. And that's driven by the ClO2. And so what we want to do is take our equilibrium constant for that reaction, and that was I think that's given in the book as well. So we could look this up to find 10 to the minus 9.21 as the equilibrium reaction there between Cn minus and HCN. Okay, so we'll need that, and then essentially we can convert and determine what our ratio of the two is. So that's where we're heading with this first part in order to find essentially to find that ratio here at pH 5. Okay. From there, we can take a look at how much Cn minus, because Cn minus is the only one that's going to react. HCN said that was negligible, so we're looking for what portion is the Cn minus, so that we know what's going on. Now the total cyanide as Cn minus is 6 milligrams per liter. So we can get the total. That would just be 6 milligrams per liter Cn minus, and then we need to take this and divide it by the molecular weight, right? So we'll just go ahead and say 0.006 grams per liter. Cn minus, and then we can divide this by the molecular weight there, which I don't have written down. Not sure why I don't have that written down here. Okay. Does anyone have that handy? Molecular weight of cyanide? Carbon and nitrogen. Nitrogen's 14, carbon is 16, or 12, I mean. So it's 28, right? 28 grams per mole. So that'll give us kind of the total molar concentration. It should be, actually somebody online is helping me here, so 0.23 millimolar here, and that sounds right to me. Well, I got something different, but perhaps what you're saying there is okay. So let me do this with you here.
26.
Should be 26. Yeah, it should be 26. You're right. Not 28. .006 divided by 26. Okay, yeah. And thank you for catching that. Okay, so yeah, that we have that then. Okay, so then we want to know essentially what fraction of this, what portion of it is the Cn minus. And the book, we can kind of take sort of a strange approach the book Solutions gives, but I think it's just a little simpler okay, well, we know that the total is Cn minus plus HCN. And so with that, we also know that our Ka is given. That was 10 to the negative 9.21, or we could look that up. And then we know that's going to be the products of the reactants for this, right? So that's going to be H plus times Cn minus divided by HCN. So with that, we can get the ratio between, the ratio that exists if we say 10 to the negative 9.21 divided by essentially the pH, 10 to the minus 6.5, and that's our ratio of Cn minus to HCN. It's going to be a fairly small number that we can see from there, and that's going to be we can just take that and multiply it by that 0.23 millimoles of total Cn minus, and that'll give us our value. So we can take that ratio and multiply it across, and then we know our actual value of Cn minus. Okay. So I'm not trusting my the solutions I have on hand at the moment, so I'm just going to do this with you over here and say let's say this is our ratio here, Cn minus divided by HCN. So this will be 10 to the negative 9.21 divided by 10 to the negative 6.5, and then we'll use this to say CN minus, oops, that times 0.00023, because that'll give us the 0.23 millimolars in molar units. Okay, so that gives us 4.48 times 10 to the minus 7 moles per liter. And I just want to see. So 4.48. Okay. So then, questions asking if the dose of chlorine dioxide determined previously, which I'll flip to that in a second, is used, what detention time is required to oxidize 99%. So we're looking for tau. Tau is the question to oxidize this stuff, 99% of this stuff, given the chlorine dioxide dose that was given. Okay, the dose was 7.23 milligrams per liter. And we were also given some information about how much was consumed, which was 6.17 milligrams per liter. So during that process, (6.17 milligrams per liter of that was consumed. And so essentially our effective concentration in that process for ClO2, kind of that concentration here at steady state, would be that difference, so 1.06 milligrams per liter. So that's the value we can use for the next step to determine essentially that hydraulic resonance time. So all this, we're still on A. Okay, with that, we can then set up our mass balance. And we can say 0 equals what's coming in, so Q times our Cn minus. And actually, you know what, I just realized the book's taking a bit of a different approach, and last time I solved this, followed that approach. I was trying to simplify it today, and I probably should not have. And the reason is because we have this total cyanide, right? Some of it's HCN, some of it's Cn minus. And if only the Cn minus is reacting, then as soon as some of it reacts away, then it equilibrates again. So some is replenished from the total pool. And so technically we ought to be accounting for that during this process. And I was trying to simplify it and just take the Cn minus. There is a way, and that's what's going on with these solutions here, where we can kind of account for the total Cn here, initial. And so I'm gonna continue. I'm gonna go back to my solutions and actually trust them. I'm so sorry. I'll explain as we go where we see this. Essentially, that fraction that is in Cn minus form is the stuff that's reacting, but we're subtracting it from the total Cn that's there. Hopefully that will make sense. Okay, but this is what's coming in terms of our mass balance. This is going to be a mass balance on total CN. So this minus what's going out, that would be the Q times total CN. And then we have what's reacting, and it's a decay reaction. So we have minus our reaction rate constant, K. So normally we would have in that volume, I'm just going to start with volume actually. So in the volume of the reactor times K times our C, right? But in this case, our C is going to be the fraction that is let's see. We also have the chlorine that's doing the reaction. So the chlorine itself needs to be there as well. That's the steady state dose. So we'll have the chlorine concentration and then times the CN concentration. And for the CN concentration, we just have the portion that is currently in the CN minus form. That's the stuff that can react. So what we're going to do here is say some fraction. I'm going to call this the alpha, alpha that is CN minus. So denoting that portion that is CN minus. That's what we solved for last time, or just a minute ago, where we got that ratio. And then multiply this by the total CN. And take that also times the chlorine dioxide concentration. So ClO2. Okay, so I'm going to simplify this and divide everything by Q. That'll get us to the point where we have tau that we're trying to solve for. So we have total initial CN. We already know what that is, minus the total CN that's in solution in the reactor that's reached equilibrium or reached a steady state, minus tau times essentially this portion in the reaction term. So K times the ClO2 times that alpha CN minus times total. So probably we could just put in the, let's see. No, I think we do have to keep the total here and keep this fraction here. So that way we're keeping the information about how much exists in total, and we're keeping in the fraction in terms of because we're at some pH and there's that equilibrium, and that equilibrium happens instantaneously, we can just use that fraction times that total. That's the way it makes the most sense. And by the way, I'm not going to have it get this complicated on an exam question. All right, so anyway, then we can solve for tau with all of this. We actually have all these pieces of information. That's where the dosing comes in, and we can then solve. So one thing we'll need to do is convert the dose. So before we do that 1.06 milligrams per liter, go ahead and multiply that. That's ClO2 times 1 mole ClO2 per this many milligrams ClO2. I'm just converting the milligrams there. That'll give us 1.57 times 10 to the minus fifth moles per liter of ClO2. Okay. From there, we can put in everything and solve for tau. And if we do that, tau will end up equaling 112 hours. Okay, so fairly complex with the issue of the equilibrium and what portion of that is reacting. But otherwise, it was in a CSTR problem. So the mass balance part, hopefully, outside of that fraction issue, hopefully was simple. Okay, part C, excuse me, says if the pH was raised to 8, what detention time would be required to meet the same, essentially the same requirements? That changes. Okay, there's a question, why didn't I use the full dose of ClO2? In the full dose was, what did it say? At 7.3. Where did it go? That's a good question. So the analysis and the stuff that part that I gave you, let me pull that up. Okay, so the book solutions that I provided says the ClO2 dose required to oxidize 1 milligram per liter was therefore, and it gave you this information, calculated 6.23 milligrams per liter, and for that case, it said to oxidize cyanide and leave a residual of 1 milligram per liter, the ClO2 dose would have to be 7.23 milligrams per liter. Okay, so we have two numbers there, that 6.23 and that 7.23 for that case. And so in our condition, trying to see where we did get the 6.17 that I'm referencing. I thought that was part of the given. What did part A ask? I should pull up the actual question here. Let me pull up the book real quick. We'll take a look at that. Okay. So in the book, doesn't really give anything extra. Okay. Let's do this then. Okay, solution manuals here. I think it'll be better for me just to try to see what they're saying about it. Okay, so that's problem 1. Okay, that was problem 2, and we're on 3. Okay, so here we're taking a look. I gave you this portion. Part B, we've stepped through most of this. we had that ratio. Okay, that's where it's coming from. So in the calculation in part A, oxidation of 99% of the initial cyanide will consume 6.23 milligrams per liter of ClO2. 99% of that 6.23 is the 6.17. So that's where that number is coming from. And the initial dose was 6.23 milligrams per liter. So what's happening is we're dosing it at 7.23 milligrams per liter. 6.23 milligrams per liter would be consumed to oxidize everything. So 99% of that gives us that 6.17. That's the amount that's immediately consumed when we add it to the reactor. Because it's a CSTR, CFSTR, the reaction that occurs, it instantly takes it down in the concentration. So whatever is at steady state inside the reactor is also what's leaving the reactor. So that leaves us with a residual left over that is doing the reaction for us in that way. That's why it's situated that way. I'm going to give you most of the credit if you used the 7.23 or whatever. So this is the book here is being, it's really revealing the depth here that we need to properly get the solution here. So anyway, I'll leave it kind of at that and just scroll through the rest of the solution if there are any other questions. Part C asks about pH 8, and without trying to hurry along a little here, it's late and we're taking a while on this problem. So basically we just do the same thing with a different pH. We have a different ratio. We expect more CN minus at pH 8, so it should be happening quicker. I think, yeah. The first one was 100 and something hours, and now this one, 112 hours, drops it down to 15.7 hours because we have more CN minus as a ratio. If we were to increase the pH even more, we expect that it's going to react quicker because there's more of it there. All right, part D then asked, come back here, for the same conditions as part B and C, what detention times would be required in a plug flow or batch reactor? Okay, so that's basically, instead of using the mass balance up there, we would go to the that type of version. And so in that case, we take a look at the reactions. We get 3 hours and 6 minutes, respectively, for the two different conditions. So just saying that it's going to react a lot quicker, and that's because we don't have that initial dilution effect for the chlorine or for the cyanide. So for both of those reasons, it's going to be a lot faster. Okay. All right, so 10.7 here, and again, I think what I'll do is walk you through the solutions instead of walk through the, try to do all the solutions right now along with you. Okay, so the pharmaceutical diclofenac has oxidized can be oxidized either by direct reaction with ozone or by reaction with hydroxyl radicals, as indicated by the following reactions. So ozone and diclofenac mix products according to some rate constant. With ozone, 10 to the 6 moles per liter, per molar per second, I mean. Or the OH radical route, where we have 7.5 times 10 to the 9th per molar per second. So you can see very, very big difference in the kinetics there, although we do expect a lot higher concentration of ozone. So part A says, in a water that contains carbonate alkalinity, compare the rates of degradation for 10 to the minus 8 moles per liter of diclofenac under the following conditions. 1 is pH 6, 20 micromolar of ozone dose. 2 is pH 8, 20 micromolar. And 3 is pH 8 with 2 micromolar ozone dose. And so really what we're looking for there is the rate of the reaction. So R of, really the R of the diclofenac. We'll say DCF, call it, for those different conditions. And so what we're looking for is kind of the overall rate of a reaction. And that's what the solutions will take us through if we take a look. And what I can do probably is put these next to it. Okay. It's readable. Good. All right. So part A. This is not the right problem. I think the right problem is here, just in a different number. Perhaps. Okay, maybe I will be solving it with you. Well, that's talking about the right thing. Hang on. Let me just... Okay, well, I'm just going to run through it as quickly as I can by hand. There's a similar example. If you need a reference point, that's 10-14. So we can get a lot of a similar problem there. But let's go ahead and work through this. So for these three different conditions, essentially what we want is kind of a system of equations here. We know a couple of the most important equations obviously are O3 plus OH minus yields us HO2 minus plus O2. The K for this reaction is 70 per molar per second. So I'm just going to list a few reactions that we may need to consider in terms of the production of hydroxyl radicals. We can then get with the ozone, HO2 minus yields us OH radicals and superoxide radical anions. The K here is 2.8 times 10 to the 6 per mole per liter, per mole per second. Okay. With that, then we want to take a look at different rates for the concentration of ozone over time, the rate of the concentration of that diflucanac dt, the concentration of OH radicals over time, and the change in the HO2 minus per time. So these are going to be our relevant reactions, and then we use Excel to essentially plot out different portions. So we can write these out as negative K. So this would be K1. If we're following, we'll label this one as K1. Up here, we'll label these, it would be K4 and K3, given the different Ks we're about to write out. Times the C of ozone, times the concentration of the difluconac, minus K3, which is the removal of ozone, K3 concentration of ozone times concentration of OH minus. So essentially what we're looking at is the things that change the concentration of ozone here. Minus K4 concentration of ozone times the concentration of this HO2 minus. Okay, so we can do that for each one of these and list them all out. The ozone one was the kind of the most complicated. Here, K1, C for ozone, because this would be the reaction with ozone itself, minus the reaction with the hydroxyl radicals, and we can essentially relate here the, so this will be K2. And we can use COH, but I think we can also, I have it written as HO2 minus, and I'm trying to figure out if that's intentional here. I think it should be OH dot. Okay, so we could continue. Each one of these has its corresponding rate, and then what we would want to do is put that into Excel to generate a bunch of time points we could sequence over time and estimate this numerically to get some estimation there. And essentially what we'd end up with is some sort of a plot for the difluconac concentration over time in seconds, and we should see something like this, or this for the different cases. Excuse me, just like that. So this one I think is 2 micromolar, and then there's another one that's right here. So this is the 2 micromolar case, and these other two are approximately the same. So essentially the deal is at this higher dose, 20 micromolars of ozone was pretty rapid, where that 2 micromolar ozone at pH 8 was not particularly effective. Part B says, what effect would carbonate alkalinity have on the degradation rate? And we see, because when we changed the pH, that wasn't the big thing that changed the rate here. You know, if we were to model all of that properly and do all of that in Excel, we end up seeing that it's not the pH changing which would create more hydroxyl radicals, because you'd end up with more of this. It's not the pH change that mattered. It's actually just the ozone concentration that mattered. And so adding carbonate alkalinity would not affect it too much, because the carbonate's going to react with hydroxyl radicals, decrease their concentration rapidly. So in this case, we would say that most of it was ozone, so it wouldn't really matter. Okay. And then part C, how much would the initial rate of diclofenac degradation differ from that calculated in part A if the solution contained 5 milligrams per liter of solids? And I have that cut off. I'm not sure why. Let's see. Did I ask for this part? I'm sure. Just A and B? Okay. I was confused. I was like, I don't have solutions here, and I think I didn't ask for it. Good. Okay. So probably more involved, again, than it should have been. I think problem 7.1 and 8.1 are a little better calibrated in that regard. Okay. So problem 7 and 8 are both adsorption problems. So 7.1, trichloroethylene TCE is an organic solvent used that is present in as a trace contaminant in many groundwaters, is quite strongly adsorbed to activated carbon. The maximum adsorption capacity for a particular activated carbon for TCE is 65 milligrams TCE per gram of carbon. When 1 liter of solution that initially contains 200 micrograms of TCE is dosed with 10 milligrams of the carbon, 15 micrograms per liter of TCE remains in solution at equilibrium. So part A, assuming the Langmuir adsorption isotherm applies and the adsorption equilibrium, find the adsorption equilibrium constant, give appropriate units. Okay, so I'm going to go ahead and take the shortcut here, pull up the solutions for this as well, because we're running out of time. Okay, so we're using the Langmuir isotherm. That's this formulation, if we were to look it up. And what we're looking for is that K, that what did it call it? It was the equilibrium constant. Yes, thank you. And so for the Langmuir isotherm, the Q, of course, that's the adsorbate density, so the amount of adsorbed stuff on the adsorbent stuff. We've got the Q max, the maximum possible amount, and then that K here. Ca is that concentration in equilibrium of the solute, and so we were given that being that 15 micrograms per liter. We were given some information about, we can find some information about the Q TCE there. Okay, so we just rearranged here for that K, for that constant, and to do so, you multiply both sides by that 1 plus this, so you get a K on each side, and then you have to simplify. So with a 1 plus K times Q over here, you'd probably take that Q and divide it from both sides. And then you'd have a situation where you have it'd be like 1 plus K over there, and then Q K Ca divided by Q TCE over on this side. So anyway, you simplify for K, do the algebra, you end up with this equation. K is Q TCE divided by Q max minus Q TCE times Ca there. So that's just going to be the algebra rearranging the Freundlich formulation for K. From there, the QTCE we know is equal to this 200 micrograms per liter minus 15 micrograms per liter. That's the amount of stuff in solution. So the 200 it's initially containing 200 micrograms in the solution, and then we know we end with 15 micrograms per liter in the solution. So that's going to be that's the amount of stuff in the dissolved condition, right? That's the amount that was removed. We're going to divide that by the 10 milligrams per liter of carbon that was added. So that's going to be that concentration of our TCE divided by the concentration of the carbon, essentially. So that'll give us that 18.5 micrograms TCE per milligrams of the activated carbon. And from there, we can use that information, plug it back into here. We have some information about that Q max. I think that was, so that says 65. So it gave us that information. The maximum adsorption capacity for that particular activated carbon was 65. Okay, so then we have all the information there, and we get a value for our adsorption constant as 0.0265 liters per microgram TCE. Okay, so then part B asks, at the end of the test, another 10 milligrams of carbon of activated carbon and 20 micrograms per liter, micrograms of TCE are added to the solution. That is, the total adsorbent and adsorbate concentrations are both doubled. Once the system re-equilibrates, will the concentration of dissolved TCE be larger, smaller, or the same as in part A? So we've added fresh carbon and fresh TCE. That means we're going to have some carbon that has a little bit of adsorption capacity remaining, but not a lot, and then a bunch of new carbon. So it might be interesting to kind of think about that before doing any calculations to say, well, what might we think there? Okay, so solutions go under the solutions, under the conditions specified in part A. We have that density. For the dissolved concentration to remain constant, the adsorption density must also remain constant, meaning the TCE and PAC would have to be added in the same ratio, so 15 micrograms per micrograms TCE per milligrams PAC. In the scenario envisioned, the ratio of added TCE to added PAC is 20 micrograms of TCE per milligram of PAC. So since the ratio is different, so the ratio at equilibrium, we found that, we'd have to add it at that same ratio in order to maintain that ratio at equilibrium. So essentially the dissolved TCE concentration and the adsorption density will both increase a little bit when we add these two in there. So essentially we just we kind of changed the ratio of them. We didn't match what was already there, so it can't continue at that same equilibrium. Okay, so part C asks a water supply is to be treated to reduce TCE concentration from 85 to 5 micrograms per liter in a batch process. What is the required dose in grams of activated carbon per liter of water? And what fraction of the adsorption capacity of the activated carbon will be used? Okay, so that's just looking for a dose of a powdered activated carbon dose requirement. So we're going to take that Q here and essentially solve for that Q, and then say, well, given that, well, so that Q will be our dose, essentially, how many micrograms, or that'll give us the amount of TCE removed per milligram of PAC. So that way we can calculate the amount of PAC required, given that we have to remove essentially 80 micrograms per liter. So that'll give us the way to find that portion. So to find that concentration of the PAC, after finding the Q there, given those parameters and that final concentration required, we have that QTCE. From here, we can solve for the concentration that was removed divided by that absorption capacity. So that's 85 minus 5 divided by that Q. That'll give us 10.5 milligrams of powdered carbon per liter as our answer there. So it's a little strange using these concentration units that are on a surface, like a mass per mass concentration, but at the end of the day, they are mass balances like we've seen in many other cases. Okay, so that's 7.1. Oh, had it all right there. Okay, so 8.1, we have some data here for the uptake of trichlorophenol, or TCP, on activated carbon. Initial TCP concentration was 100 micrograms per liter in all cases. So we have different carbon doses listed and the final concentrations provided. So given this data, which we can plot, the first thing it says is determine the best fit parameters for fitting the data with a Freundlich adsorption isotherm. So we would definitely need to go to Excel for that. In terms of exam content, I'm not going to ask you to get your computers out and start working on Excel. So don't be concerned about that. So to take a look at what they recommend as the solution, they took the data and then plotted it as essentially a log plot, so that you can take this equation and linearize it. So if you could do log Q by log C, that makes it so that we don't have to worry about that exponent. We can just use a linear regression. So that's one thing we'll notice here. They take the data and list it out here, and they go ahead and calculate, okay, well, how much of the C was adsorbed then? You can get the Q then based on that. And then they take the log of both C and Q. So that's going to give us essentially the linearization based on the data that was provided. And so when they fit it, the data looked like this, where it was pretty well linear for some time. And so you can probably use the line of best fit for all of the data except that last point. And that would be reasonable. And let's see. Given that, it asked for the best fit parameter. So with that, I think that's where they came up with these numbers here and here by taking that line of best fit. All right, so we are over time. I'm just going to finish this out as fast as I can. If you need to go, I totally understand. So part B says so an industrial plant needs to meet effluent discharge limit of 1 gram of TCP per day. How much carbon would be used per day in a CSTR in which adsorption equilibrium is reached quickly for a process flow that was 600,000 liters per day of waste containing 100 micrograms of TCP. So it's kind of building from here and asking about removal in a industrial plant. So if we follow, I did notice that the solutions have an error here. This should be 600,000, not 150,000. So discharge of 1 gram per day and a total flow of 600,000 liters per day corresponds to concentration. And if you do the math, they actually use 600,000 here. So they just had a typo. And you basically take that mass per day divided by the flow rate on a daily basis and convert micrograms to kilograms or vice versa. And you get 1.67 micrograms per liter in terms of, that's the total amount of concentration they can be discharging in their flow, right? It's just a conversion to see, okay, we're allowed 1 gram in a whole day. Here's our flow rate divided up in that whole flow. This is the concentration. According to the adsorption isotherm, at this equilibrium concentration, the adsorption density would be, so we can find a Q, given the isotherm data that we solved for. We can get that Q, and essentially that's going to be 0.036 micrograms TCP per milligrams activated carbon. Goes on. Amount of adsorbed TCP is the difference between the influent and effluent concentrations. Carbon dose required to adsorb this minimum TCP at the computed adsorption density is this. So we get an activated carbon dose, and then we take that, so that's activated carbon per liter, and then we take that multiplied by the amount of liters we're treating in a day to get 1,600 kilograms of activated carbon per day, so quite a lot. All right, so I should probably head out here, but I'll post this answer to part C here. There's probably another class coming. It's basically asking how much carbon would be required per day if the stream were treated in 2 sequential batch reactors. So I'll go ahead and post, I'll copy this solution into here if that's not already, yeah. So I'll post it in there, and I'll post those slides so you have all of that. If you have any questions or need some another time to chat, maybe Zoom or something, be happy to do it. Sorry this was rushed and less organized than I would have liked. But thanks for the semester, guys. I hope this was useful, hopefully interesting, at least sometimes. So we'll see you guys next week, Thursday at 12:30.